So when we're talking about symmetry, we're talking about how a graph looks. It's like a visual thing, which is kind of cool, right? Sometimes we don't often get that. And so this blue box at the top here is kind of laying out the types of symmetry, and we've got three different, obviously the first column's talking about the different types of symmetry. The second column tells us how we test for that type. The third column is a pictorial representation of what that type looks like. And then the fourth column is a geometric meaning, like it's basically explaining the visual part in words in that fourth column. And then I'm going to add something on the right here in terms of even and odd. So symmetry with respect to the x-axis, let's see what that looks like first. It looks like the graph is unchanged when it's reflected around the x-axis. In other words, the way I think about these ones is if we fold this graph along the x-axis, right, so we like took it and we folded it like this, those two signs would line up with each other. Right, that side above the x-axis would line directly up with that side below it. So that's visually what it looks like. And you can see what it's showing us here is that those two points being shown, which are they're on opposite sides of the x-axis, they have the same x value, but they have opposite y values. That's what's being shown there. And so the way we test for it then is the equation is unchanged when we replace y by negative y, which is literally what that graph is showing us. It doesn't matter whether we plug y or negative y in there, we get the same thing. Excuse me, we get the same x value. Symmetry with respect to the y-axis is similar, except we would want to fold it along the y, right? So if we took that y graph and we folded it like this along the y-axis, sorry, this one, where we folded it like that, the two sides would line up with each other. And so it's very similar except it's similar but opposite, right? So the y values in this graph are the same at those 2 points being shown, but they have opposite x values. And so the way we test for this type of symmetry is we replace x by negative x in the equation, and if the equation stays the same, it's symmetric with respect to the y-axis. Now this is also a type of symmetry, and so this is known as even. So even and odd functions, we say that symmetry with respect to the origin I guess I wrote that down wrong. What I want to say is even functions have symmetry with respect to the origin. That's what I wanted to say. I know that it's kind of hard to read. What I wrote there is even functions have symmetry with respect to the origin. And so saying a function is even is just another way of saying that it has symmetry with respect to the origin. And then the last type of symmetry, which is written on in the third column here, is symmetry with respect to, I'm sorry, I wrote origin there. I'm getting a little confused. Symmetry with respect to the y-axis. I'm sorry. We're talking about the y-axis on that last one. I was jumping ahead a little bit. The last one is symmetry with respect to the origin. And so this one is a little bit strange because the folding's a little bit harder to think about. But you can see that basically the graph is unchanged when it's rotated 180 degrees around the origin. So if we took this graph and we rotated it 180 degrees, so if this is my pen, rotating my pen 180 degrees is this, right? So turning it upside down. If we turned this graph halfway around, it would look the same, right? So if the graph was attached to my pen right now and I turned it like this, it would look the exact same. And so we say, so it's a little harder to kind of visualize, but the way we test for it is we do both of the previous things. So the equation is unchanged when x is replaced by negative x and y is replaced by negative y. And so we do both of those things, and if the equation stays the same, we have symmetry with respect to the origin. And as far as even and odd functions, these are odd functions. So we say that odd functions have symmetry with respect to the origin. And there's another reason they're called even and odd, which is that even functions usually have even powers and odd functions usually have odd powers. So I'll say usually because it's not always the case. And then usually odd functions have odd powers. Let me rephrase that. All odd functions have odd powers, but all odd powers don't necessarily mean odd functions. That's what I'm trying to say. And same thing with even. If we have an even function, it will have even powers, but just because we have an even power doesn't mean we have an even function. In the homework and stuff, you see more things related to symmetry, but just know you'll probably see a couple about even and odd functions, and that's just something you should kind of just be somewhat familiar with. Like, you should have heard those words before if you're going to take another math class. And so let's look at a couple examples on how we do these. Are there questions about the concepts at all before, or the pictures or anything? Oh, so notice what happened here, and too, I forgot to mention this. This graph here, this point and that point are going to line up with each other if we rotate the graph, and they have opposite both x and y values, right? That has positive x and positive y, and that has negative x and negative y. All right, let's look at one of these. So let's determine if the following equations have any types of symmetry. So we're gonna test all three of these on each one. So I'm gonna test whichever the first one is. The first one is symmetry with respect to the x-axis. So I'll say x-axis question mark. And so what you do is you replace, like it says right here, you replace y with negative y and see if the equation changes. And so we let y equal minus y in that equation. 2y minus x squared equals 1. And we'll get 2 times minus y minus x squared equals 1. And that negative y multiplies the negative 2, and it makes it a negative 2y. And so obviously the equation changed, right? It used to be positive 2y, and now it's a negative 2y. And so that means we don't have this type of symmetry. So I'll say the equation changed. So no symmetry with respect to the x-axis. If we want to test for x-axis symmetry, y-axis symmetry, so y-axis question mark, the instructions up above say replace x with negative x, right? So in this equation, let's plug in a negative x. And so when we plug in a negative x, we get 2y minus negative x squared equals 1. And you can see, remember, y-axis symmetry is the same thing as even functions, right? And even functions usually have even powers. And you can see that this one does have an even power. And so what ends up happening is this square multiplies the negative 1 in this parenthesis, and it makes it positive again, right? In other words, this then simplifies back to our original function because that square squared the negative out of there. And so then we say that we do, so the equation's unchanged. So yes, symmetry with respect to the y-axis. So we had a yes, a no, and let's do the origin. Questions about this though, at this point? So no x-axis symmetry, yes y-axis symmetry, and let's look at origin symmetry. So origin question mark. And so with the origin symmetry, you do both those things. You let x equal negative x and y equals negative y. together. And so when we do that, we get 2 times minus y minus x minus x squared. Forgot to plug in the negative there. Minus x squared equals 1. And so even though this negative is going to cancel out that first negative, I mean the square is going to cancel out the first negative, the second with the y changes it. So this changed. And so since that negative sign wasn't in our original problem, we have no symmetry with respect to the origin. Thoughts on that at all? Alright, let's do the next one then. So let's look at x-axis on this one. We'll need enough room here, so make sure you're giving yourself enough room. So x-axis on this one on the right. So we let y equal negative y. And when we do that, it ends up inside the absolute value, right? And we know that absolute values also make things positive, just like squares make things positive. And so that is going to change it back to our original function. And so because this is unchanged, this means we have symmetry with respect to the x-axis. And so another moral is not just even powers make things positive, absolute values make things positive too. So things with absolute values around them, you'll often see have one type of symmetry, one or the other. If the absolute value was, well, let me just leave it like that, yeah. What about, let's do y-axis. So if y-axis, we do the opposite, right? So we let x equal negative x in the equation. And we'll end up with absolute value of y equals minus x to the fourth. And just like the squared in the last one, so this last one had the square that made the negative positive, this one's got a fourth power that's going to make that negative positive. And so this will also be unchanged because this just becomes x to the fourth. So this is also unchanged. And that means we have symmetry with respect to the y-axis. And so what's going to happen when we plug both those things in, when we plug a negative y in and a negative x? It's going to have origin because they're going to both become positive and go back to the original problem, right? So let's look at that. Origin, we just do both of those things. So let x equal negative x, y equal negative y, and we'll get negative y in absolute value equals negative x to the fourth. And both those things are going to happen together. Those both become positive, and we end up with y absolute value equals x to the fourth. And so unchanged, so symmetry with respect to origin as well. Yeah, so this would be an interesting looking graph, this, right? It would have all kinds of symmetry. I believe it looks like an X that goes through the origin. Yeah. Questions about how we do this? Yes?
Not really like respective to whichever axis, like the way you write it, or is there a specific, like you not have a specific way you want it answered?
I would want to see something like this. You don't have to be so detailed like, oh, let x equal negative x and let y equal negative y. But on a test, I would want to see that you're testing those things. And then I would want some final answer that says it either does or doesn't have respect to each one of those. Each one of those, yeah. So it depends on what's asked. Like if I say, does this have respect? Does this have symmetry with respect to the x-axis? Then I'm only asking about that one thing. But I may just say, does this have any types of symmetry? In which case you would want to test all three of them. And yeah, I'm not going to be picky about like the exact phrasing you use, but I want some statement that says yes, it either is or isn't. Other questions? Try the last one then, please. So y equals x cubed. If you know what that looks like, you probably already know what the answer is. And if not, give it a go. See what it looks like. I'm going to think about that too. So what does this one have? I think it's got something. Let's see. So x-axis question mark. I'm going to let y equal negative y, and we get minus y equals x cubed. This equation changed. So no with respect to the x-axis. The second one, let me use red on this one. If we want to do y-axis, we would replace x with negative x, and we get y equals minus x cubed. And now this cube makes the negative stay negative, right? Because when you multiply negative 1 by itself 3 times, it stays negative. And so this is just y equals minus x cubed. It also changed. So no with respect to the y-axis. And the origin is a little bit tricky. This is the one that you want to be a little careful about. So the origin, we do both. So we end up with minus y equals minus x cubed. And I know that looks like it changed because now they both have negative signs. But if we multiply both of this equation by the same number, both sides of the equation, right? If we multiply both sides of y equals x cubed by any number, it stays the same. And so in this case, we multiply both sides of the equation by negative 1. And so this is the same thing as just y equals x cubed. Because we could just, again, we could multiply both sides of the equation by negative 1 again, and it would be the original. And so this didn't change. And so we do have with the symmetry with respect to the origin. And if we graph it, let me just throw a small graph down on each one of these. If we graph this thing, x cubed looks like this. This is a graph that we'll become familiar with. This is what x cubed looks like. And we can just see that it has symmetry with respect to the origin, right? If we rotated this graph 180 degrees, right, we just kind of like turned it upside down, it would look the exact same. And let's look at this one too. Let's graph the other ones too. I don't have a lot of space here, but let's, I'll throw a graph down above this one. This is an x squared graph, and x squared looks like this. And so if we look at that graph, we can just see that it has symmetry with respect to the y-axis, right? If we took that graph and we folded it over, it would match up with each other. And that's why we ended up with a yes right here. And this other one, this weird looking one, ends up looking kind of strange. This ends up looking like this. And so that's why we get all those symmetries, because we can fold it, right? We could take that graph and fold it like that and it line up with each other, or we could fold it like that and it would also line up with each other, or we could flip it upside down and it would also line up with each other. So we've got all those different types of symmetry going on. Questions about this, any of this stuff? So there's two types of questions you could be asked. You give an equation, and I could ask you what type of symmetry, or a graph, and ask you what, if any, type of symmetry it has. So if you go back and look at the symmetry section, you'll see that what I had said was symmetry with respect to the y-axis is the same thing as an even function. So this thing on the left here is the same as symmetry with respect to the y-axis. And on that page, what I had said was odd functions are the same thing as symmetry with respect to the origin. And you can see that in the definition here, right? This is the definition of what it means to be symmetric with respect to the y-axis. So we say a function is even if when you plug in a negative x, the function stays the same. Right? That's the definition of what y-axis symmetry is. And we say the function's odd if you plug in a negative x and everything switches around. That means that the function's the same as the origin. And so in some ways, you know, the other way to write this is that minus f of minus x is the same as the function. This is how we thought about it in the symmetry section. We thought about when you plug in a negative y and a negative x, the function stays the same. And so that's rephrasing it in a different way, but it means the same thing. And so let's just look at a couple of them. And do you remember what was a general rule of thumb for these things? I wrote down something on that page that was like, usually even functions have blank, and usually odd functions have blank. Do you guys remember that at all? It's kind of in the word. Right, what do you think even functions usually have as powers? Generalize that. 2 is an even function, but because it's an even number, yeah. Sorry, x squared I mean. So usually even functions have even powers. If there's powers at all, right? So like absolute value is an even function, but it doesn't have any powers, or has a power of 1. So it's not all the time, but usually even functions have even powers, and usually odd functions have odd powers. So be aware of that for the homework. But the way you test for it is what you do, what says right in this box. If you want to see if a function's even, we plug in a negative x and see if it stays the same, right? And then if we plug in a negative x and everything switches, that's what this one says, and that means it's an odd function. So for example, let's just do a quick, I'm going to draw two simple examples here. Let's say we have f of x equals x squared. What type of function is that? It's even. It's got a square, it's got an even power, And if we look at the graph, we already know what x squared looks like. X squared looks like this, right? And so we can just visually see that it has even properties because it's symmetric with respect to the y-axis. And moreover, we can use this property just to check, right? If we plug in a negative x, we get negative x squared. The negatives cancel out, and we just get x squared. And so you can see that the function stayed the same. This is the original function. So when I plugged in a negative x, the function didn't change, and this is implying it's an even function. And again, visually we can see it because it's symmetric with respect to the y-axis, but look at this. It doesn't matter whether we plug in an x or a negative x. Both of those two values have the same output. That's what that formula is telling us. Both of those things end up being the exact same height, showing us that it doesn't matter whether we plug in an x or a negative x, you get the same output. That's what this formula is telling us right here. Questions about that? So let's look at a real simple odd function then. What about f of x equals x to the fifth? Right, it's got odd powers. And so that's a good indication it's an odd function. If we look at what x to the fifth looks like, it looks like it's symmetric with respect to the origin. Right, that's what x to the fifth looks like. And we can test use the box at the top and just test it. If we plug in a negative x, we end up with the opposite of what we started with. And by opposite, I mean all the signs are switched. Right? We'll get a minus x to the fifth. And so this thing is the opposite of the original. Right? We started with x to the fifth, and we ended up with minus x to the fifth. And so this is an indication that it's odd. Right? And we can verify that visually. And let's say we plug in the same two x values, but positive and negative. So let's do a plus and a minus x. If we plug in the positive x, we end up with some y value. And if we plug in the negative x, we end up with the same y value, except it's negative. That's what that formula says. If we plug in a positive versus a negative x, the same number, right, you end up with the same y value, but one's positive and one's negative. That's what the formula is telling us. Questions about this before I just ask you to think about one? This makes sense, this idea? So, if you want to check, you just plug in a negative x and see whether or not the signs change. So I'm gonna write down one on the left side of the page here and ask you to think about one. So think about this one real quick. Oftentimes you can kind of just look at it and tell, just imagine plugging in a negative x. So what about this one? It's kind of a combination. The ones we just tried were super simple. This one's slightly more complicated. What's going to happen when you plug a negative x in? Just take 30 seconds and just think about that. And think about whether or not the function stays the same. Do all the signs switch? Or something in between? Maybe some signs switched, but some signs stayed the same, right? So just to be clear, when you do that, you end up with this, right? Minus x to the seventh minus 3 times minus x squared. And sort of what's the takeaway here? What happens? Yeah, one of them changes. The first one, you raise a negative to an odd power and it stays negative. But then when you raise the negative to the even power in the other one, it becomes positive. And so what we see here is this negative sign changed, which implies odd, but this negative sign stayed the same. And so we had a little of both in that one. It didn't completely stay the same, it didn't completely switch all the signs, and so this is neither. It's neither even nor odd. And so in other words, that one just doesn't have symmetry with respect to anything. If we graph that one, it's not going to be symmetric. It's going to be all over the place.